All right, take two. Hopefully this works. So we're doing 125 here. It says that was the one that was voted for essentially this week. It says a cord is wrapped around the rim of a solid cylinder of radius 0.25 meters at a constant force of 40 newtons is exerted on the cord shown as shown in the following figure. This figure right here. They're talking about this one though right now. The cylinder is mounted on frictionless bearings, so we don't need to worry about friction. And the moment of inertia is 6 kilograms meters squared. So moment of inertia of the disk is 6 kilograms meters squared. Use work energy theorem to calculate the angular velocity of the cylinder after 5 meters of the cord has been removed. So they're giving me essentially that this force is exerted over 5 meters, and that's going to be the work done basically. If the 40 Newton force is replaced by a 40 Newton weight, what is the angular velocity of the cylinder after 5 meters of the cord have unwound? All right, so okay, so basically what I'm going to do is I'm going to use, like they suggest, the work energy theorem to calculate the angular velocity from the rotational kinetic energy from part A. And then in part B, I'm actually going to say this whole thing is my system, and then I'm going to, and the Earth is going to be in there as well. And then I'm going to say essentially that I've got gravitational potential energy from that hanging mass, and that's going to convert to translational kinetic energy from the mass and rotational kinetic energy from the disk. So I'm going to use conservation of energy the second time around, but I'm going to use the work energy theorem the first time around. So that is my goal. So here is my my drawing here. So again, 6 kilograms meters squared is my moment of inertia of this disk. The radius of the disk is 0.25 meters. The force that's being exerted is 40 newtons. So again, the work done by this force is going to be converted into rotational kinetic energy of that disk. So that's me using the work energy theorem. So I'm going to start right there. The work done by that external force is going to equal the change in energy of my system. So that means that the work done, let's go ahead and plug that in. Work is force times distance times cosine theta. So it's going to be the force times the displacement. So delta x, I'm saying delta x is 5 meters. And then it's cosine of theta, but theta, I mean the force is going this way, the displacement is going this way. They're both pointing in the same directions, so it's an angle of 0. Cosine of 0 is 1, so it's just going to be a positive value there. So nothing really needs to change there. And that's going to change into rotational kinetic energy. So it's my change in rotational kinetic energy. So again, force times the displacement equals my final kinetic energy, which is 1/2 I omega squared, minus my initial kinetic energy, which was 0. The disk starts at rest. So lastly, all I got to do is isolate omega. So multiply both sides by 2. That's 2F delta x, and divide by my moment of inertia. Take the square root of both sides. That's going to be my angular velocity. So the square root of 2 times the force, which is 40, times the displacement, which was 5, divided by my moment of inertia, which they gave me was 6, and that gives me an angular velocity of, calculating, 40 times 10 divided by 6, take the square root, that's going to be 4.16, 8.16, sorry about that, 8.16 radians per second. So that's my answer for the first part. Now for the second part, I'm going to predict that, well, first off, this was my object in the first part here. So my object was just the disk, because I have some weird external force of 40 newtons that's showing up that's going to do the work that changes the disk into having rotational kinetic energy. But in this one, I think it's going to be easier actually to say the whole thing, both the mass and the disk are my system, as well as the Earth. So I got the Earth off to the side as well. That's going to be my part of my system as well. Because what I'm going to say is I got gravitational potential energy between this Earth mass system here, and that's going to be converted into translational kinetic energy from the falling mass, and then rotational kinetic energy from the disk as well. And so that means my prediction is that the disk is actually going to be less than this 8.16 radians per second. That's because couple reasons. One of them is I have more inertia here, so it's going to, given the same essentially force, 40 newtons, so that's going to make it for a smaller acceleration, so a smaller angular velocity. Or I could look at it as the same work is being put into this system, but it's being converted into both rotational and translational energy, so that energy has to be divvied up. Two ways you could really look at it. So, and neither way is necessarily wrong, and they both give you the same answer as a result. But okay, let's go into it. So basically, I've got initially here, I've got gravitational potential energy from this hanging mass. It's going to fall 5 meters, and so that means at the end, I'm going to have rotational kinetic energy plus translational kinetic energy. So again, rotational from the disk, translational from the falling mass. So let's do part B over here, and that's going to be, again, I'm using conservation of energy this time, so the initial energy equals the final energy. Let's see, I got gravitational potential energy to begin with. That's going to equal kinetic energy rotational plus kinetic energy translational. All right, so the gravitational potential energy was going to be the mass multiplied, the mass of the falling mass, multiplied by the gravitational field. That's going to be 40 newtons because that's essentially the force of the falling mass that's up there. Multiplied by the height, which is 5 meters, equals the rotational kinetic energy is 1/2 I omega squared plus 1/2 mv squared. That's equation for translational kinetic energy. So before I go any further, I do need to find out what this mass is. And I'm going to use the fact that the gravitational force is the mass times the gravitational field. So divide both sides by baby g. That's going to give me the gravitational force divided by baby g is equal to my mass. The gravitational force is the weight of the falling mass. That's 40 newtons. So it's going to be 40 newtons divided by baby g, which is 10. And that'll give me a mass of 4 kilograms. And that's going in there. Okay. All right. So the other thing I need to do is that this velocity ain't going to cut it. I need to translate that to angular velocity, and I know that the tangential velocity, or the velocity at that point there, is equal to the angular velocity multiplied by the radius of the disk, because the string is wrapped around the disk, and because the string is wrapped around the disk, the linear velocity, or the translational velocity at this point, is equal to the linear velocity, or the translational velocity of that mass, because it's essentially at the same line of action, or the same radius, outer radius as the disk there. So I can use that relationship over here. So all right, let's keep going here. It's going to be mgh equals 1/2 I, let's make it better, I omega squared plus 1/2 m, and then v is going to be omega times r squared. Well, that's going to be just omega squared times r squared, because that squared is going to distribute. So last thing I need to do is just isolate these omegas. So I'm going to factor out the omegas and then divide by everything I have left over. So it's going to be mgh equals 1/2 I plus mr squared. All that factored out with omega squared. Divide by all this nonsense, and that'll give me mgh over oh, oops. I got the 1/2 here. Okay, the 1/2 was freaking me out. So let's see. Over here, starting here, I'm going to multiply the whole thing by 2. So if I do that, that'll cancel this. It'll cancel this, and it'll give this 2. That means there's a 2 here, and there's a 2 here. So now I'm dividing by I plus mr squared. And then I'm taking the square root from this. That's going to give me omega. So it's going to be the square root of 2 times the mass, which is, well, mg is 40, because that's just the weight of the whole thing, 40 newtons, times the height, which is 5 meters, divided by the moment of inertia they gave me was 6. The mass is 4 kilograms. I calculated back over there in gray. And then lastly is the radius, which is 0.25 they gave me. Am I right about that? Yes, 0.25 squared. And so I get omega. So we got 40 times 10. Let's see. So 40 times 10, that's just 400. Divided by 0.25 squared times 4 plus 6. Take the square root and I get 8 radians per second, which is in fact less than the original one, which is what I predicted. So that's good. Yeah. So there you go. So yeah, used work energy theorem for the first one, because I had some weird external force that I didn't know what it was, so that's going to be work done. It's going to change the rotational kinetic energy. I could have used work energy theorem for the second part, but to me, the conservation of energy was easier. And yeah, so all right, hopefully that was helpful. Bye.